My name is Melody, and today I'm going to present my work in collaboration with my group members, Blake Finkernauer, Dr. Ke Ma, and Professor Letindo. My project focused on interface engineering to kinetically trap the photovoltaic phase of formamidinium lead iodide perovskite. In 2019, renewable energy provides 11% of the U.S. energy consumption. Within the renewable energy category, solar energy only contributes 9.1%. Report from the National Renewable Energy Laboratory, NREL, stated that the rooftops have the potential to generate 38.6% of the annual national electricity sale. Among them, small buildings including residential and commercial buildings has the largest share. Furthermore, solar energy can be used to supply a significant share of the world's energy because solar technology can be used in remote locations and unique applications such as portable energy sources and light harvesting tinted windows. Currently, crystalline silicon is the dominant semiconductor material used in photovoltaic technology. However, silicon solar panels require high temperature batch processing and very pure material for high efficiency solar cells. In the past decade, promising light absorbing materials called perovskite have experienced rapid development. Within only 12 years, the power conversion efficiency of perovskite solar cells has been improved from 3.8% to the most recent 25.5%, which rivals the 26.1% record efficiency of single crystal silicon solar cells that is achieved after more than 60 years of study. Impressively, here we're comparing devices made of polycrystalline perovskite to the ones made of single crystalline silicon. Perovskite have direct bandgap, in contrast of the indirect bandgap of silicon. To excite electrons, direct bandgap materials only require photons, while the indirect bandgap materials requires both photon and phonon at the same time, which is much rare. Therefore, the silicon material is made to be much thicker to increase the probability of the electron excitation. In comparison, perovskite allows 200 times less material to achieve a comparable device efficiency to silicon solar cells. The direct bandgap property, together with other advantages such as large light absorption coefficient, low temperature solution processability, were able to make high efficiency, ultra-flexible perovskite solar cells, which has generated a lot of excitement in the solar energy study. Perovskites, specifically organic inorganic halide perovskites, have ABX3 structures. A is a small cation such as methylammonium, formamidinium, or cesium. B is lead or tin cation, and X is a halide anion such as chloride, bromide, or iodide. Each B cation connects with 6 X anions to form octahedral structure, and A fits in the free space between octahedra to form the perovskite lattice structure. Formamidinium lead iodide is used in the highest performing perovskite solar cells due to its near ideal bandgap. However, the photovoltaic crystal phase of formamidinium lead iodide is only metastable. At room temperature, the non-perovskite yellow delta phase is thermodynamically more stable over the desired photovoltaic black alpha phase. By increasing the activation energy required to transform to the delta phase, we're able to kinetically trap the desired phase of FAPBI3 perovskite. Currently, the best perovskite solar cells degrade in about 6 months, which has delayed their commercialization. To solve the phase instability issue in the FAPBI3 perovskite, launching ligands are applied to the surface of the 3-dimensional perovskite. These ligands consist of 2 parts, the organic tail and the ionic terminal group. The organic tail is commonly an alkyl chain or phenyl ring, and the most common ionic terminal group is methylammonium. The organic tail can change how the ligand pack on the surface, and the hat can change how the ligand fits into the perovskite lattice structure. Furthermore, the number of carbon between the 2 parts can change the penetration depth of the hat. This changes the bonding distance and thus changes the electronic property and stability of the surface. Here is an example of a study done by Dr. Gao in our group that demonstrates the synthesis of this type of ligands. Upon heating, These ligands diffuse into the perovskite structure, and the ligand heads fill the organic cation vacancies, while the bulky organic tail line up in a uniform direction to accommodate limited space. In this way, we convert the surface of the three-dimensional perovskite layer into two-dimensional perovskites. 2D perovskites are lower dimensional material with the same octahedral structure as 3D perovskites. The difference is that the charge carriers in 2D perovskites move in the horizontal direction, since organic tail create insulating spacing and inhibit charge transportation in the vertical direction. 2D perovskites have superior stability and water resistance compared to 3D because the ligands on top protect the perovskite from moisture ingression. However, if the 2D perovskite layer is too thick, these bulky organic tail groups can block charge transportation and therefore reduce the device performance. My task is to control the type and thickness of different 2D perovskite passivating layer to tune the surface optical electronic properties and stabilize the surface. Typically, long-chain alkylammonium ligands are used to create a hydrophobic and strained interface. While this method is effective, the use of alkylammonium ligands is limited by insulating nature of alkyl chains, carbon-carbon bond rotation, and poor thermal stability of organics. Therefore, in a study of formamidinium lead iodide perovskite, we're applying ligands with different anchoring group to match the Fa vacancies in the perovskite lattice structure. In the literature, different types of anchoring groups are being studied. Here are a few examples. My research group has synthesized the pi-conjugated oligothiophenol ligands with Fa anchoring group that can be applied on our perovskite layer. The Fa anchoring group is a unique idea, and we believe that it will match the Fa vacancies in the perovskite structure. As we change the ligand structure, the solubility also changes. Therefore, we need to find a good solvent system for these ligands. To find a common good solvent system for the ligands, we tried isopropanol, ethanol, chloroform, chlorobenzene, and 2-methoxyethanol. Isopropanol and chloroform show low solubility, chlorobenzene shows medium solubility, and ethanol and 2-methoxyethanol show high solubility. However, since ethanol and 2-ME can harm the perovskite layer, we used 95% of chlorobenzene and 5% of ethanol mixed solution as the solvent. These ligands have low solubility in general, so we need to further filter the 2D perovskite precursor solution before we apply it on the three-dimensional perovskite film. We incorporated these ligands precursor solutions in solar cell devices and measured the 4 representative properties using a solar simulator. The solar simulator mimicked the sunlight illumination and tests power conversion efficiency, fill factor, voltage, and current. So far, perovskite solar cells with these ligands do not show a clear trend in device performance. We have achieved a device with power conversion efficiency of over 20%, but the variation in the fabrication process still need tighter control before making clear conclusion. In the next step of my research, my goal is to analyze and test different ligands, tune the thickness of 2D perovskite layer by varying ligand solution, concentration, and thin film annealing conditions. We can detect the 2D crystal structure and use techniques including X-ray diffraction and its emission using photoluminescence spectroscopy. Furthermore, we can characterize the ligand penetration depth using angle-dependent X-ray photoelectron spectroscopy and time-of-flight secondary ion mass spectroscopy. By characterizing and monitoring the perovskite film over time, we can understand how the ligands influence device performance and stability. We expect the ligands with Fa anchoring group and the bulky oligothiophenol to increase the device stability, which will contribute to the commercialization of perovskite solar cells. Thank you for listening.